Okay. Welcome back from lunch, everybody. Hope you had a good break. We're going to move through some of these next slides rather quickly. They are probably better for you to do on your own than for me to talk through. But we'll just sort of describe what's going on in each of them, and then we'll get to wrapping up the building a thermal model so we can sort of stay on schedule. So this slide is just working on how to build the base plates, add them to the model, contact them down to apply the heat loads to it. In this case, we have all these symbols that we've defined that have their values. And then there's a logic manager, which is used for importing the Cinda logic. So I would essentially create rectangles for the base plates, apply a heat load to the rectangle, assign it the value for the Q component, make sure that the box is checked to output to expression. And then the logic object over here, if you were to go through this part right here is looking for the behavior of the component that has a relationship to the eclipse. So basically, we're using the modulus of the current time and the period. If that's greater than the shadow entry and less than the shadow exit, then we're in eclipse, and we apply a dissipation appropriate to that, and then we would apply a different dissipation for the remaining part. So the fact that we used a expression and set it to Q component A, and then we change it's Q component A, so we would use the one for Q component H. The fact that we change Q component H here means that every time Cinda comes through the variables block, if this is changed, it will reflect that change in there if I output as an expression. If I didn't output as an expression, it would just have the value, and this wouldn't do anything. So that's why it's important to output the expression such that if you're going to change a variable as Cinda is running due to its performance or some other thing such as eclipse and in sun, you need to have that defined as a symbol rather than as a hard-coded value. Here are some more details. This handles the components K and L and deals with the fact that, okay, we want to do an orbit average version of it. So if the solution is less than 1 end-solve variable, or we want to handle the transient aspect. So this is a box that comes on for certain power for a certain amount of time and then goes into a lower power state. There are some examples down below here where there's some deliberate errors introduced. And that's done when you go through it so that you can see how to troubleshoot when Cinda tells you that, hey, this didn't work or I couldn't find this. It gives you some of the more common errors that you might get back if you're working with Cinda logic and you didn't put it in exactly correctly. So again, these are getting into more advanced capabilities using the logic objects, but when you start to understand Cinda and what's going on behind the scenes, being able to utilize the logic objects helps you connect better to Cinda without having to write inserted or included files. All right, this part right here was trying to figure out how we can apply partial MLI to a surface. What we were going to do is essentially say, all the elements that are underneath this box, we want to make insulation because we don't need that to be radiating up to the bottom of component H there. So this is a trick that can be used to basically figure out how to turn on just nodes for things, get node numbers, and so on and so forth. So if you follow these steps, you'd be able to get the listing of node numbers here that we could select. And once we know all these node numbers, and if we could see the patterns there, then we would be making the list of nodes that would be specified for the override. So overrides for surfaces are where I can say, all right, you've got nodes 1 through 1,000, but I want node 500 through 570 to have MLI, or I want 500 to 570 to be a different optical property. So those are ones that you have to apply using the override capability. So this is a way of basically being able to select some of the ones and turn it on. And so what we've done here is figure out how to turn on those nodes, identify what that range is, and then that range would be listed over here in order to specify what the optical properties are or the MLI insulation. So once you've gotten that list, one of the things to be careful of is I apply insulation to the underlying structure node, but if I'm applying an optical property override to something that has MLI, I need to specify the MLI node that will have the optical property assigned to it. Otherwise, it won't make the override as you expect it to. So if I want node 10 through 20 to be MLI and have GBK instead of a default of white paint, I need to do an override of the MLI on 10 to 20, but then override of the optical property to the 10 to 20 plus the offset that you're using for the insulation node. Clear? So this is just going through some of the steps there. Here's where you get to the optical property overrides. And then for the MLI, the overrides are over here in this bottom left-hand corner. And I'll start using the laser pointer on the screen because that makes more sense. So here are the overrides for MLI. And then here are the overrides for optical properties. One other thing that you can do, it's not demonstrated in this, but you could control whether MLI is applied to a surface or not via a symbol. So if you wanted to investigate, does this surface need or not need MLI, I could use this P button up here, and based on what that evaluates to, if it's 0, then it would be false and wouldn't apply MLI. If it's non-zero, it would be true and would apply MLI. So that's a way of being able to configure your model such that you could use a symbol to determine whether there's insulation or not on a surface. And again, down here is the reminder that if you're overriding insulation nodes, you need to make sure you specify the insulation node number, not the underlying structure. So they give you a reminder there, and I've given you the reminder, so hopefully that's enough to recall next time you have to do it. All right, this was moving on to component H, where we put in the dissipation. We also added a heater. Heaters have different ways of behaving depending on how you want it to. There's a proportional capability, so this would add heat proportionally based on the T low to the T high. At T high, it's 0 watts. At T low, it's the maximum number, and otherwise it's linear between them. There's the behavior for what to do in steady state. I would always advise to use the proportional with the damp factor. Setting to midpoint temperatures or setting the power just generally is assuming you know knowledge that you don't already know. If I wanted to set it to a power, then I already know my duty cycle. Why am I running the model? Setting it to the midpoint temperature creates a bit of a problem that it might actually apply cooling, because it's going to just hold that node as a boundary node. And if you tell it it's going to come on at minus 20, and it would really be at plus 40, it'll cool it to minus 20 by taking heat out of the node because it just knows it's a boundary node. It doesn't know that there's a heater there. So by and large, I would avoid any of these other settings except for the proportional unless you really have a compelling need to do it. Also up here, they have something called the register append string. This is good to not accept the default, give it some name that means something. That way when you look at some of the registers or if you output some of the registers, you can determine which heater that belongs to, because if it's just A13CB, that doesn't tell you anything, much like the names for the RAD-Ks. The other thing that you can do as a trick sometimes is if you wanted to take a heater and turn it into a heat load or turn it off, so you either wanted to fail it on or fail it off, you can do that and set the set points either really, really high, such that you're always below that and the heater will come on, or really, really low, such that you're always above that and the heater stays off. So that's a way that if you set your set points as symbols and you want to look at failed heater scenarios, either on or off, you can do that with just changing a symbol. And that's listed down here. All right, this section will be going through how we build the pyramid. This is where we use that refine elements that I showed you a little earlier. So we start off and make a quad element here, and then we refine it and get 4 more elements, and we refine those again and get 16 elements on each side, and then do the same trick that we did before, delete out the ones in the middle, move some nodes, and create our geometry. This one was an area where it did make more sense to use a conductor to tie this structure down to the deck than a contactor, because there were discrete bolt points where this mounted. So it was 4 at the corners and 4 at the mid sides. So generally speaking, I tend to use contactors between surfaces more than conductors, but if conductors are at a discrete bolt location, then I tend to use a conductor. The reason you prefer to use contactors is if the mesh underneath changes, doesn't really matter. The contactor will still make contact. But if I change the mesh underneath, all of a sudden now the nodes have been redefined, and I have an orphan node that isn't really part of it, so I have to reconnect that conductor to new nodes, new node numbers as it is. So by and large, I tend to use contactors as opposed to conductors. This was going through adding the component N, and so we were basically figuring out how to do this. So it's a hemisphere on top, hemisphere on the bottom, and a mid-band there. One of the things this was demonstrating was how to use aliases. Aliases are where you don't know what the property is yet or what the optical property is, and so you put in a placeholder for it. You can think of it as a symbol for properties. And so when I define my case set, I then specify what the property is. So I might make an alias called radiator coating, and then in one case set it'll be white paint, in another case set it'll be silver Teflon, another case set it'll be black paint. And so it's a way of letting you have variability for material and optical properties using aliases. I think this is fine to use for models as you're developing them, but I would strongly suggest that when you're ready to deliver a model to somebody else, remove aliases, because it should be known at that point whether it's silver Teflon or white paint, or whether it's aluminum or titanium. So anyways, that's just some details about aliases. It's also something you can do as you hover over the alias. It will tell you what the alias is, so you can see what it's set to. The other piece of advice that I would offer is anytime you create an alias, name it as alias underscore something. That way, all of your aliases bubble up together and you know that this is an alias. If you just called it silver Teflon, then you don't know whether it's an optical property or an alias for it. This is one of the harder concepts to consider. They have what they call X scaling and Y scaling, or U scaling and V scaling. And what this does is it allows you to apply a mask along a length to something. So what this is doing is it's basically trying to say, I've got a scale factor of 1 applied at this edge, and then I've got a scale factor of 1 applied at this corner, but then in between it, from this section in is 0. So I'm really just trying to say there's bolted connections here and bolted connections here, but not in the middle. And so you could use this with the base plate to say, okay, I've only got bolts, at this corner, at the 2 midpoints, and then this corner and this corner. So you could still have a contactor, but minimize the areas where it will make contact by applying a 0 or a 1 scaling. So what this does is basically taking the length, dividing it by 1, and normalizing it to a 0 to 1 value. You can specify what this is. So this was looking at around the circumference of component N. I had 4 tabs, at 0, 90, 180, 270, and so this is trying to establish those 4 locations where it would make contact to the underlying surface. So not used very often, but if you wanted to go through the effort to do that, this is a capability that's there in Thermal Desktop. Here, this was showing some of the areas where you had some cut through, and you might need to adjust some of the nodes as you do it. Usually not a problem. So yeah, it cuts through, but radiatively it's small. It's not going to be much of a difference there. So you could probably live with it. If you couldn't, then you mesh it a little better. But for a contactor, that's an edge contactor, it doesn't really matter if this is the edge here, whether it's making contact on this side or this side. It's just a tolerance for the distance. So it doesn't matter this side or that side. For face contactors, it does, because it could be that I only make contact on this face, and if the face I have is over here, it won't make contact. So if you use the point algorithm for face contactors or edge nodes, then it's just a distance, it doesn't matter. If you're using the face contactor, then the side does matter. And this is some places where applying the thickness can be a problem, because if it applies the thickness, then it expands the plane where it is, and now all of a sudden you might not make contact anymore because the thickness has applied, the plane has shifted the plane where it's trying to make contact, and now you're not on the right side anymore. So that's the reason I tend not to use the thickness. This part right here was displaying the crossing and window that we talked about a little earlier. Let's see. Heater node locations. Okay. All right. This was, again, just applying some. So yeah, that's one other kind of quirk. In Thermal Desktop, when you apply a heater, the button over on the side is really only apply a heater to a surface. And you could then go in and say, okay, it's not a surface, it's nodes, and do it. There is also an RC heater node command that you can type in that will then say, okay, I'm expecting you to input nodes to apply a heater to and not a surface. So there are differences. So a heat load, you've got a heat load on a node, a heat load on a surface, heat load on a solid. Heaters, if you use the button and the icon on the toolbar, it's just heaters to a surface. So if you need to apply heaters to nodes instead, then use the heater node command. If you find you're doing that enough, you could actually go in, create a button, assign it that command, give it an icon, and customize the toolbar to have your own RC heater node button and use that. So that is also capable in AutoCAD. So if you've done all the work and gotten to this point, this is what the model would look like. You know, it's a CAD on the left, the thermal model on the right. And so now let's talk a little bit about the solar array. I will admit this is an area where I don't have particularly good understanding of how the azimuth and elevation trackers work together to get things right. You know, it's a bit of a mystery to me. I don't understand all the kinematics well, but it seems to work okay. But you would define an elevation and then a azimuth. The azimuth would be you know, minus 90 to plus 90, and the elevation would be, or actually the elevation would be minus 90 to plus 90. The azimuth would be 360 degrees around. So in this case, we're going to apply two contactors, or two trackers rather, and they're going to be nested. So one tracker is going to move based on another tracker tracking the sun. So one of the things that happens in this particular model is when you get to a beta 90, if I can see here, you get to a beta 90, you know, this is not a unique solution. Any rotation of this about the axis pointing out of the screen would still satisfy it. So that's why we have that lock array for beta 90 that basically says disable this tracker when I tell you to. So when you run a beta 90 case, it makes it so it's always pointed away and isn't cutting across and blocking the view here, because this is sort of a singularity, if you will. So let's try to go through and see if I can get this right and demonstrate how to set up the trackers. All right, so we're back over here. Let's delete our meshers. Okay, so I don't need this. So I'm just going to go to the actual model and see how it looks. Okay. So if I turn on the trackers, so I'm list here by assemblies and trackers. And so I see I got this tracker azimuth, and attached to tracker azimuth is tracker elevation, and then attached to tracker elevation is the solar arrays. So if I turn all this on, and then make sure that the global visibility for trackers and assemblies is on, then you can see here that I've got this one inside. This is my azimuth. And I've got this one programmed. So this program is where I say, all right, how do you want it to behave based on a symbol or an expression that you put in here? So if this lock beta 90 is equal to 0, then it's supposed to be tracking the sun. If it's 3, or if it's not 0, then it's supposed to lock it in whatever position you would have there. So in this case, I've got it programmed. It's supposed to go from 0 to 360. It is active. I could make this inactive, and then it's just going to be more of an assembly, whether it's working in the sun mode or the shade mode. And so that's this inner tracker. And then the outer tracker, the elevation, is going to behave differently. So this is now, again, tracking the sun. It's not programmed, but it has a range from -90 to +90, and again, only works in the sun. So in order to attach geometry to a tracker or to an assembly, you have these commands over here. So once you've attached geometry to a tracker, you can't attach it to another tracker without detaching it first. So when I was setting this up, I first made the elevation, then I made the, first made the azimuth, then I made the elevation. I attached the elevation to the azimuth, and then I attached the solar array surfaces to the elevation. And so depending on the beta angle that I'm at, so let's take a cold beta 30 and we'll display the orbit. So you can see that the array is moving and is tracking and staying locked onto the sun even as my nadir point changes. And so, if you rotate around and look at the side view, there's the angle, and it's doing the azimuth and the elevation to get the array locked on. I honestly can't say I understand how it knows to do that. If somebody's a kinematics expert, maybe you can explain it to me afterwards. But let's change the beta angle and show that it still works. So if I select a different orbit, sorry, that's the beta 75. Let's take the beta 30, set current, display orbit. Okay. So now you can see here, this one's not doing anything because it's in the shade. You see that in the shadow cone, but whoops. The rest of the time, it's doing what it's supposed to. And you can ignore this blue cylinder. This is over here, the work that we were doing earlier. But you can see that it's got a rotation here and then the elevation that gets there. So when I go to a beta 90, that's where it would look kind of screwy unless I have the flag set. So set this to current, display the orbit. And so here you can see that, well, it's cutting across this. I don't want that. I want it pointed away in its normal orientation. So if I view this from the sun, there you can see it's not really doing what I would want it to do. But if I were to set the lock beta 0 or lock array beta 90, set it equal to 1 for this beta 90, then when I update it, it should be pointed back out again if I did it right. And there you can see it's pointed away and staying locked. So what happened is if I look now at that tracker, come back in and look at the azimuth tracker, you can see that it's -90 is where it is at the angle, and the program says to lock it, don't let it move. And so this is how we handled the behavior that would otherwise have resulted in things not behaving the way we wanted to. All right, so that's trackers and assemblies. One other thing you can do for assemblies, you can drag and drop things in here. So if I had an assembly here and I wanted to move all these in, I could select all these and drag them and drop them onto another assembly that would then assign it there. So that is an option sometimes for organizing things. Assemblies also have the advantage that you could tie them to a symbol for rotations. And so, for example, on the wide field instrument on Roman, we have an element wheel. And in order to put the correct optic element into the beam, we have a rotation angle for that. And so the whole element wheel All the nodes assigned to it, any surfaces that are there, are assigned to the assembly. The assembly has a rotation. Clearly, the z-axis of that is going to be through the motor axis, and so we can rotate the wheel by doing that. Assemblies are also a good way of grouping things together. If you want to say, hey, I want to move this whole instrument, I could assign it all to one assembly, and then all I have to do is move the assembly. Everything attached to it will move with it as well. So assemblies are a way of organizing your geometry, but not necessarily required. But if you're trying to move something, through a symbol or anything like that, assemblies are a good way to do it. There's also an option in Thermal Desktop called Fast Spin. So if you have a rotating reflector or something like that, or a dish that's moving quickly, many revolutions per orbital position, you can set it up such that you have that assembly, it's tied to a symbol, and then you can set the fast spin option in Thermal Desktop to say, I want you to change this symbol, go through 12 different positions and fire 5,000 rays at each position. And so for each orbital position, it will say, okay, I'm going to solve 5,000 rays here, 5,000 rays here, 5,000 rays here, 5,000 rays here. So what you're doing is you're effectively smearing an average of the RAD-K views over 60,000 rays if you fired 5,000 at each of 12 positions to get an effective, what the scene is as this is rotating very quickly. Not something you want to use for a slow slew. If I've got a barbecue roll of, 1 revolution per orbit, well, then I'm just going to have the slow clocking at different orbital positions. But for a fast spin, where it's spun around many times at each orbital position, it helps you with doing that. One trick, if you're doing that, for the error associated with the RAD-Ks or the heat rates, set the value to 0. Because if you don't, it may reach that error after it's fired 35,000 rays. You needed it to fire 60,000 rays, and so you didn't do all of the positions. So set the error to 0 if you're going to do that. You'll fire the maximum number of rays, but that will give you equal weighting at each spin position for the fast spin option. All right. Okay, so here we see the different views, being able to show the planet, which analysis group, the vehicle, and things like that. So if I come back over to Thermal Desktop, we were just showing this now. I want to show the view from the sun. Here's the basic. I could set some of the parameters here to say show the planet, show the continents with the Earth. Maybe I want the orbit positions to be in there, and I want the shadow cone to be shown. And so now you get little prettier pictures for your presentations. You've got your ability to rotate around. Shadow cone is solid as opposed to see-through. And you can do it. If you need to make the vehicle a little bit bigger, that one hides over here. Under this, show vehicle, model scale factor. Let's say I want to make this a little smaller here. The analysis group that you use, so whatever surfaces are present would be here. I know there have been some times where I have a very, very large model, and trying to visualize it with all of the guts and everything hiding inside is just too much for it to try to graphically do. So I have a lighter weight radiation group that just has the surfaces that are visible externally to do that. You can animate this. I believe you can actually save it as an AVI file. You can view it at a particular position. You can view it at all the positions. So I could set all of these and get what it's doing at each position. So there are a number of options that you have here for being able to display your vehicle in an orbital configuration. There are different viewpoints that you have. You've got, from the sun. You've got from a star, from the ascending node, from planet side. So these are good. They're okay if you really need it particular, but usually, just rotating it around to get what you need is probably good enough for those purposes. But if you want to, the view from the sun is usually the direct one that I'm most interested in, so you can really see exactly what it is. All right, so moving on, we'll talk a little bit about the HGA boom, and I'll demonstrate this because this is an area where it's not necessarily intuitive how to get here. So back at the main model, let's take the boom that's over here. So I'm going to use the grips and extend this to the other length. Oh, that's the origin. Okay, another trick. I'm going to move this along here. I want this to line up, so I'm going to move this along here. I'm going to take this end here and extend it to the end point of here. Okay, that's now made it this long. Now I'm going to take this and move it from the base point to here. Come on. And now I can take this and extend the boom this length. Okay, so what you can do sometimes, make this too long, extend it to the beginning, move it to the beginning, and then extend it to the end there. So that's a good shortcut trick. You can use that for rectangles and any other surfaces where you're trying to change the lengths and things like that. So you'll notice I've got these grip points here. And there are different behaviors of these depending on what you set. So there's an RC grip boundary. And what that does is now instead of having the grip points, it lets me adjust the boundaries between the nodes or the node locations. So I could take this and move it to here instead, and now the locations of the nodes has changed. So this is a way of being able to do things instead of having to type it in through the boundaries over here to the subdivision. You can adjust it by dragging points. So let's say that this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes long. So we'll make it equal. Okay. So using the grip boundaries, I can adjust a node location or a node boundary. So this node location, I might want to say move it to, right here instead. Why didn't I do that? No, never mind. Let's go back. Okay, yeah. All right, so sorry, got lost in my work here. All right, so we're going to copy this again. Same things, but instead of sizing these locations here to line up with that, there was a way to do this. I'm getting lost. So suppose I want this node. Sorry, got to do the grip boundaries. Okay, so this is, I want to make this 4 nodes along here. Okay, so suppose I want this node to line up with this piece here and this node to line up with that piece there. I can come here and say, let's take the grip, adjust the node location to line up with this. And adjust this node location. Let's turn those off. and then this node location here to line up with this midpoint. Okay. So now the node locations, if I look at them, aren't moving. All right, we'll move past this. The lesson in all this was that you can move the node locations, but you can't make, it ends up making the node boundaries be kind of crazy. So you can see that this node boundary here ends right there, but this one's much wider, this one's much wider, and this one's a little bit shallower. So what I've found that I tend to do is rather than try to get nodes on a surface like this to line up with these points, is to just make smaller pieces in between, and then I can really control the nodalization along it. It shows up a little bit better in this image right here. So let's just go full screen on that. Where the node here lines up with it, and the node here lines up with it, but you can see that the boundaries, the boundary lines between it, because it's equal sides of this, the boundary for this node winds up almost all the way here at the end. And so it's a tiny little area associated with node 4. Whereas on this one, it's equal parts to each of this cylinder, it's equal parts to each of this cylinder, and equal parts to this cylinder. So it winds up making the nodal boundaries a little bit better for where you've got the node boundaries versus the node locations. I've never been a big fan of the having to specify the node boundary as opposed to specifying the node location, because the node location to me is where I want something to be. That's where I'm trying to put a node to merge it with some other geometry. Making me specify the midpoint between two nodes means that I can't always put the node at the location I want it to be. They opted to do it that way. I'm not sure why, but they did. Another thing with the grips, there's a RC grip boundary, and then there's RC grips key points. Oops. Key point here. What this does is it would let you re-specify the origin point, the axis point, starting angle point, things like that. So when you first created the object and you specified the origin and the axis and the starting angle, this will let you re-specify that if you wanted to. So sometimes if you find that the grips are being displayed but they're not what you expect, check the RC grip boundary or RC grips key point or RC grips parameter, and they are specific to a surface. So when you select a surface, it toggles through each of those and it keeps track of what that is. It's a very seldom used command, but good to know that it's there, particularly if somebody else knew about it and used it and you didn't, and you're trying to stretch something and all it's doing is changing nodal boundaries. It's good to know how to get back to what you expect it to be. All right, so this would then just continue on with the rest of the building of the model. We would create the parabola dishes here. We would add the solid RC solids here to represent the component D that was, make contactors for it, view things from the sun. So this is where we would add a closeout because, viewing the bottom of these from the sun says, okay, I know it's going to get hot. So we put a closeout here with some MLI around it, attach that to the ESPA. So it's not really a deck, but it's a closeout. We put silver Teflon on it in order to minimize the solar absorptivity for it. And then I believe that was it for building the bus. This next part shows the insertion of a model from a delivered model into what you have. So one of the things to check is make sure that the units are the same, and that's not the thermal desktop units, but the AutoCAD units. So if the model that you got was in inches and you're working in meters, it will, when you insert a block, it will try to do the scaling for you. So you want to make sure that if that's not intended, that you say, okay, if it's inches, make it inches. If it's meters, make it meters. The command I always use for this is classic insert. There's a new insert command in AutoCAD 2021 that I haven't found to behave quite as well as I'd like it to, so I always fall back to the classic insert. By and large, you're better off to use this classic insert command than to try to copy it to the clipboard and paste it in. The reason for that is there are things called domain tag sets that are essentially definitions of groups that may hold surfaces or nodes or solids or things like that in it. But they're not an object that you can copy to the clipboard. They're defined as part of the AutoCAD database, but it's not an object that you can select. So if you copy a model and paste it in, you'll get all the objects you can select, but the tag domain sets got lost. If you insert it, then it reads through the database and it knows, hey, there are tag domain sets I need to bring in here as well. And the reason that you want to use the classic insert is that when I insert a model into another one, there are things called handles. Handles are the unique identifiers for each AutoCAD object. The handles get changed when you insert it. So I'm at a rectangle named AB1 in my source model. I insert it, it becomes CEFD1. And now CEFD1 is the same as AD1, but the tag domain set only knows AD1. So it doesn't have a link anymore to it. So if you have lost your tag domain sets, it's very difficult to recreate them in your destination model if the handles have all changed, because that's how it communicates. That's how it knows these surfaces belong in this tag domain set. So always, always, always use the classic insert as opposed to pasting or copying and pasting unless you're sure that you don't need any tag domain sets. So what we were demonstrating in this part is basically how to bring in the instrument model, which had the brackets and then the dummy instruments, and they had two domain tag sets here, instrument bracket and instrument surfaces. Both of these we ended up using, so we contacted from the edges at the ports to the instrument brackets in order to establish the contact there, and that's what this is doing. So makes it easier to select things. Tag domain sets are also useful for turning on and off and controlling visibility of stuff. And they're very useful when you're having to do mapping between a thermal model and a structural model. Because when you set up the post-processing data mapper, if you have tag domain sets defined, now I can control the subsets of my model and what they're mapping to as subset groups in the structural model. So I make sure that where I've got an interface, okay, well, this is mapping to the structural counterpart to that, and this is mapping to the structural counterpart, and I don't have to worry about, is the structural counterpart here grabbing a thermal part here, because there's a slight offset or mismatch between them. So we use tag domain sets extensively when we're doing our mapping between structures and thermals models to make sure that we're getting the right thing mapping to the right thing each time. And it's also good for controlling visibility because I can turn on and off, the primary mirror, secondary mirror, the struts, forward metering structure, the outer barrel assembly, because they're all tag domain sets. So you can think of them as groups. There are AutoCAD groups, but they do not come in when you insert a model. So you could do the same thing by defining a group and having it, but when you insert that model in, the group is lost. So you're better off to use the tag domain sets because they preserve the information that's contained in the source model when you bring it into the destination model. All right, so here is the pictures of the nearly completed model, CAD on the left and thermal model stuff on the right. So we go through now, we think we've got everything done, so we go through the model checks. So I'll just go ahead and just sort of show what you would look for. And this is where you go through extensively all the capabilities of the model browser. So what I would have is, what are the different ways that I can visualize my model? Let's first turn off the CAD. We don't need that. We're just looking for thermal. I've got everything here. So let's go ahead and delete all of the stuff that we were playing around with. So edit, list by submodel. And I'll delete all of my new stuff here. Actually, we'll delete it. All right, so went through the model browser. So many different ways I can look at the model. I can list it by submodel ID, can show any non-graphical objects, so logic objects, optical properties, thermophysical properties, case sets. I can list it by the analysis group. So what radiation analysis groups do I have? What all's in there? You know, do I have the right surfaces? Do I have the right active sides assigned to the surfaces that are in there? I can list it by optical properties. So, you know, I want to see all the surfaces that are silver Teflon. Let me display only that. You know, here I've got a default. I don't know what that is. I'd want to see why I have a default in there. And it turns out it's the instrument brackets. I can list it by thermophysical properties. So I can see where do I have aluminum, where do I have titanium, where do I have MLI assigned. You can do surfaces and solids. This basically utilizes the conductor submodel to group things together, whereas the list by submodel ID uses the node submodel and the surfaces and elements that are associated with it. But if I list the surfaces and solids here, I could look, okay, there's all these quad elements for component C mount, and so on and so forth. I can list by contactors, so I can show where do I have all my contactors made. If you really know your model well, you know, you could take the contactor tree and say, let me take everything here. Why do I have a deck 1 still? Oh, it's components, okay. I could say, let me take this, and I'm going to right-click to bring up the context menu, and I can say, show contactor markers. And so it'll give you the places where it's got some errors or things that it doesn't like. You know, but now, if I know where I'm supposed to have all of my interfaces, I can hide the surfaces, and now I can sort of rotate around my model and see, do I have contact everywhere I expect to? You know, what are all these lines? Well, you know, here are all the avionics attached to the deck. This looks like it's the place where I had one of those ones. Here's the vertical one. Here's the horizontal. There are some little areas in here that are yellow. So yeah, there's some red, but there's some places where it's making contact. You know, this would be my outer edge deck. You know, so I've got deck 1, deck 2. Deck 3 is down here. These are the component ends attached to the deck. Down here, I've got my closeout attached to the deck. You know, here are the 4 ports where the instrument brackets attach. So if you really know your model well, or if you wanted to look at subsets of it, you know, you can see, am I making contact where I expect to make contact, which establishes that I've got the conductivity network that I expect to get. I can visualize by the assemblies or trackers. Do I have the right things assigned in the order? You know, so are the solar panels attached to the correct tracker? I can visualize by all the conductors that I have. Okay, so boom, I've got, okay, the dishes to the boom. Here I've got my 8 bolts from the component C pyramid deck back down. I can look at heaters. You know, what heaters do I have in here? These are places where adding those comments is very helpful. So, you know, this heater without this comment doesn't really tell me much, but putting the comment in says, oh, okay, there's my component H survival heater. Here's my component N1 through N2. It's a good idea, I think, to put just some basic comments after it of, well, what are my thermostat set points? Is it proportional or thermostatic? How many watts for the heater? So, you know, I can kind of look at my documentation here if I have just taken a little bit of time to specify what these are. You know, just for satisfying curiosity's sake, this is the handle for this object. So there's that 2.7 or 2D7C. So if I were to insert this into another model, this would change. So that's the handle. So if you see that kind of hexadecimal number, that's the handle that AutoCAD uses. So here are my survival heaters. I can look at the heat loads. You know, so component A, component B, component D, so on and so forth. Orienters, we didn't talk about those. Orienters are used to specify the X, Y, and Z orientations for solid elements. So if you have an anisotropic property whose Kx, Ky, and Kz are different, and you make a solid element, well, you need to define what's X, what's Y, what's Z for it. For a planar element, it will assume that the X is the X direction, the Y is the Y direction. I'm not sure exactly what it does for a conic, for a rotated surface. I would guess the X is the circumferential and the Y is the axial. Measurement points we didn't talk to either. Measurement points are a very clever addition that was put in quite a few years ago. But what it does is I can create a physical measurement point and then locate it in space here. So this is where I'm going to put a thermocouple, or this is where my thermistor is for flight. And what it does is it's agnostic, or it doesn't care about the topography, the mesh underneath it. It's going to figure out where that point projects onto the surfaces that it can make contact with, and then determine the temperature at that location. So now there's no longer a need to have to line up my nodes with where my thermocouples are for testing. I can just put a measure there, and it will do the calculations to figure out what that temperature needs to be there. It's basically using the same algorithm that is used for the mapping of structural grid points onto thermal surfaces. So using those shape functions, it figures out the point here and knows the temperatures at the corners. So it will do the math to figure out, well, what's the temperature at that location, same way that the contours are drawn. This is all fluid stuff. I am not an expert in FlowCAD, so if you have any questions on that, I'll do the best I can to answer it, but definitely not my area. You have meshers, you have importers from TD Direct, these mesh displayers and post-processing data mappers. These are where you would have your post-processing mapper for a structural model. And then one of the last ones that's really useful is the symbols and expression usage. So before you run a model, you'll always want to check here, symbols referenced but not defined in the symbol manager. So did you insert a model? Is it referencing a symbol that you never brought in the symbols for? In this case, it seems there are always two of them that they have, loop count and end loop S. These are really Cinda things, not symbols. So I'm not sure why they keep doing that, but you would want to check here and see, are there any symbols that are referenced that are going to default to a value of 1 that I haven't defined? But otherwise, you can look at general and see, okay, well, here are all my symbols. How are they used? So Q component D tells you the value for it, and I can expand this and say, oh, okay, it's assigned to the heat load. And I could look at the lock array here. Okay, it's used in in these various case sets and the tracker. I can look at the hot case. Where's hot case being used? Oh, it's in all the case sets. So this is an excellent way to track, are my symbols attached to objects that are doing something different because the symbol has changed. Here are all your symbols for orbital stuff. These don't tend to be attached to any objects, but you can see there's an exception here. HR period is here in these case sets. So sometimes they can't get used. But this is a very good way to see where your symbol's being used. One of the things I didn't go over with the symbols is you can put these into different groups. So this is just in general, but I could take all of these and say, you know what, these are change group. I have to make a new group. So you right click up here, add new group. We'll call it dissipations. And so now I can say, let's take all these Q comps and put them in dissipations. And so now I can keep together all my dissipations, all my heater set points, all the things associated with instrument A, all the things associated with instrument B. A good way to organize your model. Again, if you look in the model browser, now you can see there's the dissipations, and now all the dissipations are there. So it shows you that hierarchy. If you look in the symbol manager, or sorry, the case sets, I think it also will show you the global symbol list, but I could also say, just show me the dissipations, or just show me the general ones. So you can use those dissipations to try to get to subsets of lists, because when you get to a big model, this list can get very long when you've got everybody's symbols in there. So having them grouped together is a useful capability. Likewise, you can group together case sets here. I don't think I talked about that. I've got all my hot cases grouped together. I've got all my cold cases grouped together. To do this, you would just, as I'm doing this, if I change the name or group here, I can just type a new group name in here and it'll pop up. If you want something in a different group, you can just take it, drag it, and drop it. Whoops. You can drag it and drop it there, and it'll now show up there instead. So good ways to organize your model and just help keep things a little bit easier to manage. Let's see, did we talk about everything else? Oh yeah, last one here. If you have the tag domain sets, you can list by here, domain tag sets. So here's instrument brackets, and it shows you what objects are in it, and then it shows you what references it. So in this case, there's an edge contactor referencing instrument brackets, and it shows me all the objects there. Instrument surfaces just has objects in it, but no references to it. So this might be something that's used for visualization purposes, but doesn't have a contactor or a heat load or anything like that applied to it. So those are all the model checks you'd want to go through before you push go on the model, because you want to save the time and not find out the problems after you've run it. You want to find out the problems before you've run it. So definitely worth the time to sort of go through with a fine-tooth comb and see, is everything as I expect it to be, before you spend the time to calculate all the ray trace and then find, oh, wait, I forgot to put the right property on this side. So a couple other things if you want to visualize. We've already shown where MLI is, but I could say, well, show me all the alpha properties. So here I can see what are my the properties for alpha. I can look at the properties for emissivity. One of the other things that I don't think I discussed, but that's pretty handy, under the preferences, there is a thickness wireframe. So what this does is if you're looking at the surfaces, you can see there's kind of a wireframe thickness shown here. If I turn off that thicknesses wireframe, you won't see that anymore. Oops, wrong button. Okay, so there, it's just the surface. So what that's very useful to do is when you're trying to compare it to the CAD, now I can see, is my CAD roughly fall within this envelope? So this is a good way to see, oh, did I forget to, change the thickness from the 1 meter default? And I get this huge area there. So this is a good way to check and see, does my model, my 2D models expanded in the thickness directions sort of line up with my CAD, which is generally thin-shelled elements or thin-shelled surfaces. So that's another good check to do. Contactor checks we already talked about. You can look and see what's the conductivity of things. There are also, let's see, under the model checks, you can display by the optical property color. So if you kind of make white paint be white and make germanium black Kapton be gray and make Kapton be orange and make black paint be black, silver Teflon be silver or white, then you can display something that looks like it. There's also some handy things here to check and see if there are any Ku, Kv, Kw multipliers. These are ways when you have assigned a surface to kind of add a anisotropy or anisotropic behavior without making the material anisotropic. So if I want to say, hey, this composite is really twice as conductive in this direction as this other direction, I could do a Ky multiplier of 2, even though the property is isotropic. Or if I wanted to say honeycomb has a density multiplier, let me knock that down. So you can check some of those things here to see whether they have values or not. Specific keys. So a variety of things here, all under model checks. Listing duplicate nodes. We've been through showing free edges quite a bit. Contactor markers. Calculate mass. This is a handy one. Shows you the mass of your each of your submodels as well as the insulation. So this is good when you've got to check it against a master equipment list. See if you've got anything that's way too heavy. By and large, our thermal models tend to underrepresent mass. Usually that's okay because we're more worried about if there's too much mass, it will dampen out anything. If we're trying to be stable, we don't want to overdamp the system. We'd rather underdamp the system. If it responds too fast and it's still within requirements, we're okay. But there are some times that you might have to worry if you had a control system that didn't respond properly, if you were too light. That might be something to do. And then there's this check overlapping surfaces. If you happen to have two surfaces that overlap like this, and they're too close together, when the ray comes in and hits it, which one is it supposed to assign to? So this is a good way to check whether you've got things that radiatively might be giving you problematic results. Unfortunately, I think it only gives you one side of the equation. It tells you which surfaces overlap, but not which surfaces are overlapped. You can find that information in the log file when it runs that, but it's not something where they give you, here are all the overlapped surfaces and here are all the overlapping surfaces. But it will create a group of all the overlapped surfaces, which you can display and see, okay, yeah, I see where all these are coming in and going. So those will be some of the checks that you would run, active sides and so on and so forth, before you get to the model. All right. All right, so I think that is the end of the demonstration of what I would be doing actively up here on Thermal Desktop. So.